We have a long-standing fascination with talking across years. In films like Interstellar, director Christopher Nolan uses the idea to drive the emotional core of the story. But if we move away from the cinematic drama, we find a specific physics puzzle. What actually happens if you try to exploit a wormhole to send a message into the past? Take two planets separated by 10 light-years, connected instantly by a wormhole. Step through, look back through a telescope, and you see a decade-old image due to light speed lag. A light pulse sent back might seem to arrive exactly when you left. This is an optical illusion. You are seeing light speed lag, not a reversal of time. Spatial shortcuts don't break the forward flow of the universe on their own. Physics treats true temporal travel as a matter of manipulating time itself, relying on the rules of general relativity first established by Albert Einstein. This led physicist Kip Thorne to model a traversable wormhole that functions as more than just a shortcut through space. Thorne's model requires clock desynchronization. If one mouth of the wormhole is placed near intense gravity, it experiences severe time dilation. Stepping into this older end allows you to exit the younger end at an earlier moment in history. While macroscopic physics allows for this loop, it creates a logical contradiction that threatens to unravel the entire sequence of events. This is the grandfather paradox. It occurs when a message sent backward alters the past, preventing the message from ever being sent. To resolve this, theorists propose the chronology protection conjecture, suggesting the universe forbids any physical path that would lead to a paradox. It's an impossible cycle. If a message stops an event, the sender in the future no longer has a reason to send the warning. If the warning isn't sent, the event happens anyway. Classical physics cannot survive this loop. To find a stable solution, we have to look at how information behaves at the quantum scale. Researchers from MIT and Cornell University recently modeled a mathematical workaround for this specific problem. They found that quantum mechanics allows for a self-consistent causal loop, where the future and the past must agree on a single outcome. The process, called amplified probabilistic teleportation, begins with a receiver in the past storing a quantumly linked particle. Years later, the sender attaches their message to the future half of that same particle pair. This interaction forces the timeline into a closed circuit. Unlike classical physics, this quantum model treats the past and future as a single interdependent state. The math here is probabilistic. It calculates every possible outcome and finds that paradoxical results have a probability of 0. The loop literally cannot close if the message erases its own cause. In this way, the quantum realm acts as an automatic immune system. It simply makes inconsistent information mathematically impossible to transmit. This research confirms that backward communication is theoretically possible, but it carries a significant mathematical cost. The transmission behaves like an incredibly noisy channel. The requirements for self-consistency are so strict that only a small fraction of the original data bits can successfully emerge in the past. This mathematical ceiling limits the scale of what can be sent, contrasting with the fluid, effortless history rewriting seen in fiction. The universe may permit a text to the past, but it protects the timeline by heavily taxing and corrupting the information that makes the journey. While we don't have access to traversable wormholes, this math is already being applied to the most extreme environments in the cosmos. It addresses the black hole information paradox, the decades-long debate over whether data is permanently destroyed when it falls into a singularity. The MIT and Cornell quantum loop formula gives physicists a concrete tool to calculate exactly how much information could survive the trip into and back out of a collapsing black hole. By defining the strict mathematical limits of a paradox, we have found a new way to measure the data that remains hidden within a singularity.